I want to try to move things along a little bit. So let's hop over here. Okay. Last time, we started talking about series. What's the series of a sequence? So this is itself a sequence. What's its value at n? Exactly. Okay, so it's itself a sequence. And so if we say we had this definition, series converges, or series limit, series converges. So I don't need parentheses on this. Let's make it really lean-like. This is a prop. What's the prop? What does it mean for a series to converge? We can go straight to, I heard Iman maybe? C. Exactly. The sequence converges, but not the sequence A, but the sequence of partial sums of series A. Okay. So let's hit the big, there's a little discussion of what's his face and the other guy, Simplicio, and let's just have this discussion. We don't need to read this. Okay. So when does a series converge? I mean, this is like a massive, massive question. It's basically all of analysis, like, or maybe half of analysis. When does a series converge? So we saw last time we saw that if a series does converge, series conv A, then what can we say about the individual terms? They go to 0. Okay, that's easy. Did we do anything else last time? Do we have time for more things? What else did we prove last time? Better remember? Well, let's talk about, well, we'll get to what else we did last time in a second. Let's talk about rearrangements. So does it matter? The main question, does it matter in what order you add things up? All right, so Simplicio asks Socrates, and Socrates says, here's a matrix M. It's an infinite matrix, in fact, doubly infinite matrix, infinite horizontally, infinite vertically. It's upper triangular, so it's all zeros below the main diagonal. The diagonal is all -1s forever. And on the off diagonal, you have a half just above the diagonal, and then a quarter next to that, and an eighth next to that, and a 16th next to that, and so on. So this is a quarter, this is an eighth, this is a 16th, this is a quarter, it's a quarter, this is a half, -1. Okay? Does everybody see what this matrix is? And the question is, what is the sum of the entries in the matrix? So Simplicio says no problem. Let's sum the rows. So what's the sum of the rows? So this is -1 plus a half plus a quarter plus an eighth and so on. What does that sum to? 0. Easy. How about the second row? The second row is 0 plus -1 plus a half plus a quarter. 0. Okay. And the next row is 0 plus 0 plus a half plus blah, blah, blah. 0. Okay, so all the rows sum to 0. And then if we sum all the rows, 0. Okay, so the sum of the matrix entries is 0. No problem. Easy question. Next. Not so easy because, but let's try it the other way around. Wait a second. That was just one way to do it, is to go across and down. Let's go down and across. So if we sum down, what's -1 plus 0 plus a bunch of zeros? -1, and a half plus -1 plus a bunch of zeros. -1/2. And a quarter plus a half plus -1 plus a bunch of zeros. -1/4. And -1/8. And so on. And what does that sum to? -2. So which is it? So this is bad. If we can prove -2 equals 0, this is bad. We've broken mathematics and we have to fix it. Something.
I think this issue comes from the fact that you have like two different like degrees of freedom that you kind of like to play with.
I can see that the two different degrees of freedom is what makes it feel that way, but actually you can sum this any which way. You can turn this into a linear sum by doing this kind of thing. Let me not have that there. The fact that n cross n is still countable, which is what that argument was just showing, it's not the linearity, it's not the lack of linearity in this matrix. It's something else, Joe?
How do we know that addition is infinite?
Well, we just found, so main idea, main observation, addition is not commutative. When you put the word infinite in front. Infinite addition is not commutative. Finite addition is always commutative. Infinite addition, it matters in what order you put things. Okay? What is the reason that it matters? Not, I'll put here necessarily. Not necessarily commutative. It might be commutative in certain situations. When is it commutative? So this is what we're going to build up to today. We're going to completely answer this question. I want to move our discussion along. So I'm going to try another little experiment where instead of going to the game server, we do more of it live and throw the like annoying technical things that need to be proved. We're just going to throw dilemmas, and those lemmas will become homework. Let's see if that's a way to make some serious progress here. Okay, so without giving the whole thing away, let's jump to problem 1. And problem 1, okay, so there's a new concept, definition. This is called absolute, a series is absolutely convergent, not just convergent, but absolutely convergent. Suhas.
Yes.
Throw a guess.
Maybe it's because of the fact that there's like infinitely many negative ones. So like there's no point having all the terms get like smaller at some point, which is like what convergence is.
So that's definitely involved. That is absolutely involved. And if we had put those negative ones, we could have just summed down the diagonal first, and then tried to sum, in some other crazy order. We could have done all kinds of crazy things. Brandon?
I was gonna say, 'cause like for your previous question about like when it is commutative, it seemed like when the series is like all positive or the same, I guess, same sign term, then it is commutative, but we're not ultimately inside, then it seems like that would make it not commutative.
Very good. Very good. So let's introduce the concept to say those words. That concept is a sequence is absolutely convergent. So a sequence. Why can't I write sequence? A is absolutely convergent. Which we will call abs seq conv, abs series conv rather. Sorry, a sequence, the series of a sequence. So really we would say a series, or given an, the series summation an is absolutely convergent, which we'll call abs series converges. So we have series converge. Series conv is simply that the series of A converges, and now we have something called abs series conv if the sequence of absolute values converges. And so the technical, you'll see here, the technical thing is just series converges of not the original sequence, but the sequence of absolute values. Okay, i.e., abs series conv of a sequence A is a prop which is determined by whether or not not the sequence convergence, but the series convergence, and not of A itself, but of the absolute value of A function. Okay. And let's build up some technology about this. So our theorem, our first theorem, what did I call this? Conv of, okay, so this is conv of abs conv. That's the name of this theorem. And what do you think it says?
Series is absolutely. Then it's also just regular.
Exactly right. The name gives it away a little bit. So we have a sequence, which we can figure out from context. That's why I'm putting the curly brackets. We will assume HA that abs series conv A. So the series in absolute values converges. And then we'll need to prove, our goal is to prove that the series itself does converge. Series conv A. Okay? Does this statement make sense? Let's try to figure this out in natural language. So what we know, again, what we know is that the series absolute value of n converges. And what we want to know is that the original series also converges. Any ideas, Suhas?
Like, they can, like, you get, that there is like some. Well, I know you definitely have to use like triangle inequality, because like, it's just like, you sum that, and it's less rank up to the sum of absolute values.
Yep.
And you know, like, at some point, there's gonna be like, it's gonna differ from the limit by less than epsilon. And then,
What limit? If this thing converges, so it converges to some limit, let's say L. So what's the limit for this one? Is it absolute value of L? No, that doesn't work. We don't know what this converges to. It converges to all kinds of different things, right? Like, just think about any sequence that converges and then throw in a couple of minus signs at random places. You're going to change the value of the limit. Not the tail, or maybe the tail too, depending on how many minus signs you throw in. Maybe you just throw in a couple of early minus signs. You completely can change the value almost arbitrarily. Not quite. Do we have a way of showing convergence even if we don't know what the limit might be? Cauchy, exactly. Cauchy, back to the rescue. Cauchy solves the problem twice, or I don't know, 10 times by now. So the way to show that something converges, if you don't know what it's trying to converge to, is to try to establish Cauchy. So idea, we have no clue where series n is supposed to converge to, is supposed to converge. So instead of trying to prove that it converges somewhere where you don't know where, you try to prove that it's Cauchy. So instead, let's try to prove that it's Cauchy. Okay, i.e., we're given some epsilon, and n and m are large. Never mind, we don't know how large yet. However large they need to be. We'll need to show that a sum, so what will we need to show? Let me not give it away yet. Jeffrey.
It's kind of like the sum of like all the garbage in between is less than epsilon.
Right. The mth term of the sequence of partial sums is a sum as k goes from 0 to m minus 1 of ak. That's the mth term. The nth term is a sum as k goes from 0 to n minus 1 of ak. And we'll need to show that these two things differ by at most epsilon. Now, what's important about these two things? What is this sum? This difference? Exactly. N to m minus 1 of ak. And then let's put the absolute values. Okay, so we want to show, let me put the absolute values. We want to show that this sum. So we have A, right? A is some sequence. I don't know what it's doing. I want to know that if I take the terms from n to m, or m minus 1, let's say m, but not inclusive. If I take these terms and I add them all up, they had better be so small. I mean, this is not to scale or something. They'd better be so small that their sum is less than epsilon once I get far enough out. Go.
Absolute value of A of n gets arbitrarily close to 0 since it converges.
Yes.
So we bound that sum by the sum of all the absolute values, and we can make each of those arbitrarily equal to 0, and then make that less than epsilon.
You're very close. You're saying you can you know that this series converges, and so the terms themselves will be less than like epsilon, but they won't be less than epsilon over the distance between n and m. You're very, very close, Jeffrey.
You don't care to bound it by like epsilon over distance or whatever, because if you use triangle inequality, the thing on the bottom is always going to be less than or equal to like it's less than or equal to just the sum of the absolute value of n.
Okay, so we're going to need this. We definitely need to, what should we call this? Helper lemma. Well, it would be called abs add if it wasn't in a series. So how about series abs add or something? Series abs add or sum abs add. I don't know, whatever you want to call it. All right, great. We're going to need that. And sure, yeah, we can prove this. And why will this be less than epsilon? Ivan?
That's just by the hypothesis.
It's almost by the hypothesis. Yes. And Suhas?
So will give you absolute value of that series plus an epsilon. Like
Yes, yes.
And then you know the sum is non-negative, so you can just.
But where am I getting right now? All I know is that this goes to some L.
Wait, I thought we were using the Cauchy.
We're using the Cauchy definition here.
Yeah.
But we have the Cauchy definition here. So we actually need to use the Cauchyness twice. Brandon, is that what you?
I was gonna say,
yeah.
if it's converted.
Exactly, exactly. So it suffices, because Cauchy is if and only if, it suffices to prove Cauchy to establish this convergence, but we have this Cauchy because of this convergence. And this Cauchy says exactly that the difference, but what is the difference? By the same argument, the difference will be exactly what you guys said. It'll be this thing, except with absolute values will be less than epsilon, but that difference is the absolute value of the AKs. Okay, so we have a sketch of the idea. So let me just finish the argument. Idea, use Cauchy again. Do we have a name for this hypothesis? HA or something? by HA, the series of absolute values is Cauchy, So the absolute value of the sum of the absolute values up to m minus 1 minus the absolute value of the sum of the absolute values up to n minus 1 is less than epsilon. But this difference, again, is equal to the sum from n to m minus 1 of the absolute values. And then its absolute value is less than epsilon, and this value is less than the absolute value. We don't even need to drop the absolute values. We can just say anything is always less than its absolute value, and this is less than epsilon, and this is less than this, which is equal to that. Okay, does that make sense? Let's write a human proof and then convert it into a lean proof. So human proof. So let epsilon be given. It suffices to produce some capital N such that for all n greater than capital N and for all m at least n, well, the absolute value of m, a sum up to m minus 1, if I don't put a lower, okay, I'll put the 0. Why not? It doesn't cost that much to put a 0. This difference, which by the way is equal to this difference, this sum, is less than epsilon. From HA, we know, and words like we know, are going to take 3 lines of lean code. They're hiding something. We know that similarly, and words like similarly, the sum of n of absolute value of AK from m to m minus 1 is less than epsilon. Well, with what value of little n and little m and capital N? Like, what value of capital N are we going to need? Joe?
The same one.
The same one. The same one. Exactly. Using that, the same value, or the same value. This is a really poorly written. This is not a proof. This is a sketch. From HA, using the same value of epsilon, we get an N. Use it. So that this thing. But from whatever we call this, series abs add, the sum of the AKs is at most the sum of the AKs, which is at most the absolute value of the sum of the absolute value of AKs, and that's not something you would usually write as a human being. And that's less than epsilon. Okay, let's try to do it now a little bit more formally. Should we jump straight to the lean, or should we write it by hand first? Jump straight to the lean? Akil.
How would we do that, the first step?
This first step.
Yeah.
I haven't shown you yet. That's why I think we should jump straight to the lean. Okay, so the key thing that we haven't talked about is, and I didn't write it here, there's something called, I did open FinSet. So to say, I'll just write it here, to say sum as k ranges from n to m minus 1 of anything, bk, you write this, summation k in an interval that's closed on the left and open on the right, n m. So instead of saying is in range n, you say interval, capital I, closed, open, n, it's closed at n, including n. It's open at m, so you only sum up to m minus 1, bk. Okay, that's a little bit of syntax. And so we're going to have a bunch of things that we have to put together. All right, so why is this true? So intro epsilon. H epsilon. Actually, we can't intro because we have series converges. Yeah, so we have something called we have a theorem called converges of is Cauchy. Now that was a theorem that applied to, if we look at the game board. Oh, come on. Give me full access to all the theorems so I can click on it. Series converges or what? Converges? Oh, I didn't even put it in because I didn't want us to have access to it. Right. There was a theorem called converges of is Cauchy, which only applied to rational sequences. This was for sequences to the rationals, and this was by construction of the real numbers. But then we proved completeness of R. I think I forgot to name it at that time. I have now named it seq conv of is Cauchy. So this is just convergence. This is sequence convergence. Of course, it's the same thing, but now this applies to real values. This is for functions from the naturals to the reals. And the reason this can't be put in the same framework, why can't I prove both of these are two theorems? We used to have maps from n to x. And we wouldn't prove two theorems twice if one was for rational sequences and one was for real sequences. Why did I split this one? Well, first of all, we use the first one for the second one. Second of all, they're true for different reasons. The reason rational sequences, Cauchy sequences, converge to real values is because that's what real numbers are. The reason real value sequences converge to real values is because of the completeness of the real numbers. So not only is the statement, the reason I can't prove this in one fell swoop with one statement that goes from n to x is because it's not true in one fell swoop. It's true for completely different reasons for this sequence versus for that sequence. Okay. All right. So I think I can just apply. Let's try just to show you that such a thing exists. Seq conv of is Cauchy. Yeah, it doesn't know how to synthesize things, but we do have it. So let's try applying it. Okay. So after I apply this, I got to turn off Copilot. It's a little too trigger happy. We want to think, not just see what it says. Okay, you can see this in the back, Roger? It's big enough. So the goal has changed from series convergence to is Cauchy of the series. So now we can give me an epsilon, intro epsilon h epsilon. Okay, there exists an n, so that yada yada. Where am I supposed to get the capital N? HA, but HA says sequence converges or series converges, which says sequence converges, which means there exists an L. How am I supposed to stick an epsilon into that? Yes, and what theorem does that? Yes, is Cauchy of seq conv, which now I fixed the name and I fixed the fact that A is implied. Okay, so if I now apply is Cauchy of seq conv, apply this at HA. No, come on, don't autocomplete. HA has changed to is Cauchy the series of after that. Okay, so it's an if and only if, but for different reasons. We knew long ago that if a sequence is convergent, then it's Cauchy. And now we also know that if it's Cauchy, then it's convergent. That's the completeness. And you just notice that we're applying different theorems. One is in the goal, one is in the hypothesis. We have the hypothesis, so we want to go to being Cauchy. In the goal, we want to prove convergence, but it's enough to prove Cauchy. Okay, so specialize. Or I don't even need to specialize. What's the next thing I can do? Based on our sketch, choose. Yep. Let's choose NHN using HA fed with epsilon and H epsilon. That gives us capital N, and it gives us this Cauchy condition. Okay, So far, so good. All right, so use that capital N, give me little n and little m. As usual, little n is greater than capital N and little m is greater than little n. How about this difference of series? Let's throw a little lemma. So this is going to be homework. Theorem. What should we call this theorem? Difference of sequences or something? Different series? Diff of series. So I have a sequence A, whatever it is. Does it need to be explicit? I think it does need to be explicit. I think I need integers, natural numbers, n and m. And then the series A up to m minus the series of A up to n is equal to what? Iman? Exactly. Okay. How are you going to prove this? I do. It's not possible to prove this without that hypothesis. So this is one of the dangers of coming up with exercises on the fly is, and now n and m can be implied because they can be inferred from this hypothesis. You see that? That's going to make our lives a little bit easier. Yeah, I definitely need to know that n is less than or equal to m. So that says that a difference of series is this. Okay. Now let's go here and rewrite by that. Rewrite diff of series. Oh, and I have to feed into it. It'll know what sequence, it should figure out what sequence it is, but why is n less than or equal to m? That's h and m. Oops. H and m. So that we had a second goal. It allowed the rewrite, but it gave us a second goal. Okay. I also want that at HA. So that's capital HN, right? I'm going to specialize capital HN to, you see what I'm doing? Capital H, I want the same thing for the absolute values. I got the goal to say that the sum is less than n. I want to have a hypothesis that the sum is less than n. So let's do that with HN. So specialize HN to what value of little n? And why is it bigger than capital N? And what value of little m? And yada yada, okay? So HM is this series. And now let's rewrite this at HN. And now I know that this absolute value is less than that absolute value. What do we want to do next? Bring the absolute values inside, right? I want to bring these absolute values inside of here. So we were going to make that a theorem, another homework theorem. That theorem is called, what do we say? Series abs add. Series abs add. And maybe it has the same conditions. I have some function and I have that n is less than m. Then what? I guess we need to say that the sum of k in ICO and m of AK in absolute value is less than or equal to the same thing, sum k in ICO and m of the absolute value of AK. And I'll sorry out that proof. Question? Okay. Is the interval closed at the left and open at the right? So it's a sum from n to m plus 1, m minus 1 now. Okay, I'm in.
Don't you not need that demonstration? If 0 is equal to 0.
So you're right that ICO is general enough that it will deal with it either way. Let's make our lives easier for your proof, that you don't have to split it into cases according to one or the other, because we have this condition. You're right that if you were designing a library and you wanted a very general theorem, you wouldn't include a condition that you don't need. But I'll make your homework a little bit easier if we do it this way. Why can't I spell homework? Okay. So now I'm going to apply. I'm going to apply this, or I'll just say, should I apply it? No, I'm just going to say it. Have a fact, which is this. And this is by apply series abs add to A, which it should know, and an M, and then the fact that H is less than M. Okay, so we know that we can take the absolute values here, pull them inside. We know that the absolute value of the sum of the absolute values is less than epsilon. Let's add one more thing to the, let's call this fact 1 and have F2, which is very simply that this thing is at most itself with absolute values. And it's going to complain if I leave a space there by bound or something. Come on. Oh, two absolute value signs next to each other. It's not happy about that. So that's an easy one. You just put parentheses. And now why is this true? Linear. We're going to go from here to F1, F1 to F2, and F2 to Hn. Linearith, F1, F2, Hn. No more things to be sorry about. Okay, so now you know what 2 of your homework problems will be. Brandon.
When you say, you mean for this Friday or
Next Friday.
next Friday?
Wait, next Friday. Okay, cool. So what have we learned? We've learned that if a series converges absolutely, then it actually converges. All right, let's go back to what else can we say? So we're trying to understand. Let's go back to our observation here. So if this were to converge absolutely, then we would be golden. And of course, it doesn't converge absolutely because the second you take absolute values, you're adding up, however you do this, you're adding up +1 infinitely often. By the way, you're also adding up a half infinitely often. You're also adding up a quarter infinitely often. So the fact that it converges in any direction is kind of a miracle. Okay. Here's another thing. Do you guys remember, you took like Calc 2 or BC or whatever, the C of the BC is series, sequences in series. And one of the things you learned was the alternating test. So what does the alternating test say? Recall from high school, recall from whatever, calculus, the alternating series test, Daniel?
If it alternates and like the absolute series.
Yes, exactly. Let's say it like this. If A is antitone, exactly, decreasing. So monotonically decreasing and decreasing to 0 and seek lim A0, then what?
-1.
Right. The series that sends n to -1 to the n, an, the alternating series converges. Yeah, then series converges of this. Okay. So if we have an alternating, it's funny. It's like we know that if a sequence converges, if a series converges, then the terms go to 0. We know that the converse is not true. You can have sequences going to 0 whose series diverge, 1 over n. The harmonic series is our favorite example of that. But if you, as long as it's some decreasing sequence, decreasing to 0, and by the way, of course, it doesn't have to be exactly antitone. It could be eventually antitone, since all that matters is what happens at the tail. But let's prove the simpler theorem. We'll assume that A is antitone, and the alternating series must therefore converge. Let's see if we can prove that. So let's look at the statement. So that's going to be level 2. Let's just look at the skeleton. Here's the alternating series test. We have a sequence A. We know that it's antitone. We know that its limit is 0. So it's decreasing down to 0. Then we want to see that the alternating series converges. Why is this true? So let's think about this. The series is, why is this true? The series is, A0 minus A1 plus A2 minus A3 minus plus A4 minus A5. Daniel.
There was each term, you're kind of like staying in this A0 minus A1 range.
Yes.
And you're like, because A2 is less than A0, you don't go back up. So it's kind of bounded by both A0 and A1.
Okay. Kind of. Suhas? I'm with you.
So can you first like prove that all terms of A are always non-negative?
Okay, very good. Very good. So we'll need a little side lemma. For all n, an is non-negative. Just a second, Jeffrey.
Yeah, and then you can use this with like the absolutely convergent thing, and then you can bound like the series you wish to prove by that like the absolutely convergent, because you know that like just the series A is like absolutely convergent.
I didn't assume that. That's the amazing thing about this theorem. Let's make, well, I said this in words, but let's make this observation. I'm just going to write it all down. Recall.
Oh.
Yeah, this is really important. If the sequence converges, the series converges, then the ANs go to 0, but not the converse. Not the converse. But here, we're saying if the ANs go down to 0, then I can't say the series converges, but the alternating series converges. This is a very deep distinction, Jeffrey.
I think kind of building off of that, so like, suppose you take the partial sum through like some term, let's say like A sub k.
Yes.
And then basically because it's like alternating and the magnitudes are decreasing, the sum of that is going to be bounded by like the sum through k minus 1 and the sum through k minus 2. It's like somewhere in between there.
Very good. Let's make that precise. I like where you're going with it. Let's make it precise. Suhas?
You like use that with like the repeatedness, so like it's like the range of values keeps like decreasing, or like, and then like you somehow I don't know. I don't have it.
You guys are close. Jeffrey, can you make what you said precise, or Daniel? You said a very key thing, which was that this will somehow be close if I take the last 2 terms out. What happens when we group these in pairs? What can you say about each of these? They're all positive. I don't know that they're decreasing, but they're all positive.
Well, shouldn't each of those terms decrease because of specific factor?
But I don't know the difference.
Oh,
Yeah, I don't know the difference between them is decreasing. Roger?
So like, I would explain that.
Yes.
It's, not mostly. But like, if you like separate the A0 and you group it like -1,
But if you group it this way,
it's like, it's
The term is always negative.
The terms are always negative.
So it's like,
Uh,
Look at-
so S2n, the subsequence of SNs where you take the even values, you're adding up, if you stop at any even value, I guess, what am I saying? S2n does stop at an even value. S2 stops at, it includes 0 and 1, but not 2. So that's just this first sum is S2, and this sum is S4. There's 4 terms in it. S2n is monotonically increasing, is monotone, and S2n plus 1 is antitone, If I stop at odd values, I'm decreasing, is antitone. Okay, S2n is monotone. Is it bounded? So we're going to have to prove all of these things. Jeffrey?
I think yes, because like, if you like add on, it's always less than S2n plus like the next term.
It's less than, but I want it bounded above. If it's monotone but bounded above, what do we know about sequences that are monotone and bounded above?
So S sub 2n is always less than or equal to like, wait.
So this one stops at an odd value. S2n stops at an odd value. It starts at 0, 0 to 1, 2 to 3, 4 to 5. I claim that this is always bounded by A0. Because this term is negative, and this term is negative, and this last term is negative. Okay, so this is monotone and bounded. How about S2n plus 1? It's antitone, so this is bounded by A0.
The other one is bound by A0.
For example. Yeah, or even just bounded by 0.
Sure.
Because, well, I guess, yeah, it's bounded by 0. 0 works. 0 works because I'm going to stop at an odd value. So when 2n plus 1, when n is equal to 1, the first term is A0. A0 is non-negative. Then I'm going to add 2 more terms. And the difference of those 2 terms is A2 minus A1. So in the even one, I take 2 terms. In the odd one, you can think I take 2 terms and 1 more. I mean, that's another way of doing it. You take 2 terms and 1 more, but not 2 more.
Like, you're still grouping them. Oh, it's like an even number of terms that you're grouping it like the way you grouped S2n plus 1, like.
If you like, no, these are negative.
Right.
So that's bad for proving positivity. But these are positive. So you think 2n plus 1 is 2n, and then 1 more term.
Right.
Each of these is positive. an minus, the A0 minus an, this is positive. This is positive. This is positive. So I take a bunch of terms that are positive, and then 1 more term, which is positive. Or at least non-negative.
If you were to write out S2n plus 1, like the same way you wrote out S2n there,
Here.
yeah. So,
That wouldn't be good because I have an A0, which is positive, and then a bunch of negative terms. And I don't know that when I subtract off all these negative terms, I don't have this last term.
I'm asking like what the equivalent representation. What's the argument right here?
Yeah, let me do it. S2n plus 1 is equal to A0 minus A1 plus A2 minus A3 plus A 2n minus 1 plus A2n A2n, it will come with a minus sign. And then there's one more term. Does that make sense? And I'm saying that all of these things, every term that's bracketed is non-negative. So the whole thing's non-negative. Okay, Daniel?
Explain like.
Yeah, the monotonicity is that the even ones are adding up a bunch of positive terms. And I think, did we already prove that if a series has positive terms, then it's monotone? Or did I put that as a homework problem? Okay, if you don't know that theorem yet, it's because I put it as a homework problem.
Oh,
Okay.
but then when we actually, so, okay, so we're grouping it differently when we're showing monotonicity versus when we're showing it's bounded.
Exactly,
Okay.
exactly. So that's what I was going to write here, is that these things are less than 0. Grouping it this way is less than 0.
So we look at the second grouping to show that it's bounded, but then we look at the first grouping for monotone.
Exactly, exactly. The monotonicity comes from the first grouping, the boundedness comes from the second grouping. And in the same way, the antitonicity comes from the second grouping, but the boundedness comes from the first grouping with one more term. Okay, so S2n is monotone and bounded, S2n plus 1 is antitone and bounded below. Suhas?
Wait, so you know S2n, that's like,
S2n converges to some value L. S2n plus 1 converges down to some value M. Why? What's that? Yeah, you can try a subsequence theorem. Say it again. Which one? Algebraic limit theorem.
Oh, wait, no, you don't. What am I talking about?
They're not the, yeah, they're not the same thing. Hyman? The monotone and bounded, it says it's Cauchy, and is Cauchy means it has a limit, so we'll get a limit L out of it. And same thing with antitone and bounded below. But how do we get these two things to be equal? We need one more idea. Suhas.
so maybe take like S2n and S2n plus 1, and you know they differ by like a very small, like.
Okay, so there's what's the general principle lemma? If I have a sequence AN going to L, however it does, and I have another sequence BN going to M, and the sequence AN minus BN goes to 0, then L equals M. In fact, this is the coherence of the quotient under quotienting of equivalence sequences of Cauchy sequences. The fact that we can take the fact that if you have some sequence converging to a real number, some Cauchy sequence converging to a real number, you have some other Cauchy sequence converging to some other real number, but those two Cauchy sequences are equivalent,
Oh, right.
then those real numbers are the same. Okay, we haven't actually proved that, so I'll make that a little homework lemma. And then, so we put those two together, and that says that the S2n and S2n plus 1 converge to L equals M. They both converge to L, and so Sn converges to L.
How would I feel? Not like that. Not like that.
Well, it's a definition that we can only make if we prove that it's a coherent definition, if it's a well-defined definition. Yeah, Suhas.
So I was wondering, like, Can't you say by like the subsequence thing that like S of n converges to L and S of n converges to M and then.
But I don't know that there is a limit. You're right that limits are unique. But if I have a sequence whose one partial sum is going to L and another partial sum is going to L, is going to M, there's no reason the sequence of partial sums. Just cook it up so that you have, I mean, you get to change whatever you want. You get to change the term by whatever you want. Right? What about it? So all I'm saying is this is a general lemma. Anytime you have one sequence converges to L, another sequence converges to M, and their difference converges to 0, then L and M have to be the same. That's a general lemma. Without this lemma, if you can take whatever, if you just have, you tell me you have a sequence, and you tell me along the evens, your subsequence of your sequence of partial sums converges to L. Along the odds, your sequence of partial sums converges to M. I don't have a way of concluding that Ln and M are equal without appealing to something like this.
I think it's last.
The last implication, very good, very good. So we have that S2n and S2n plus 1 both converge to L. Why does that tell us that Sn converges to L? Jeffrey. Sabe.
Subsequence converges to one. Then like that has to be like unique. So just like something about like bounded.
But what is it exactly? Yeah, so how do we where does this equality come from? So S2n goes to L and S2n plus 1 goes to L implies Y, Sn goes to L. Suhas.
Like Sn is just like constructed by altering the terms of S2n and S2n plus 1.
Yes.
So like.
Daniel?
I mean, I think if you, I mean, oh my God, I think you could like do it directly pretty easily.
Yes.
Like if you just have, like, for any sequence, you know, if all the even terms, all the odd terms go to L, you can get that usually by one goal.
With what?
By one goal.
Even easier?
Like you have two things, you just take like.
Yes.
You have it from.
There'll be an N1 from this and an N2 from this, and we'll take N greater than the max or the sum. And then why is this true? By cases. Okay, by cases, you know, N even or odd. Okay, those are all the things that we have to put together to get this proof. And half of these things you wouldn't see if you just did it in natural language.
So when we just look at the series or the sequence like -1 plus 1 minus 1 plus 1, we're not allowed to just like group things, right? Because it like breaks.
We certainly are.
Well, before like we got into series, when we were just like convergence.
Sure.
If we grouped it one way, we got 0. If we grouped it like another way, we got. Or like
Oh, exactly right. That's a great example. That's the +1 -1 sequence has even partial sums 0, 1 and -1, 1 and -1, and odd partial sums 1.
So
the evens are monotonic and bounded because they're constant at 0. The odds are monotonic and bounded because they're constant at 1.
So that would fail for the step of n minus n. So,
Exactly right. And it would fail because the first assumption was that the ANs themselves go to 0. Which the +1 -1 doesn't.
I know that we proved that if the sequence converges, that any subsequence converges to the same one.
Yes.
But in the context of, like, say we have a sequence that's a series, isn't the converse true?
So the converse is true only if, I mean, look at the example we just looked at. We have a subsequence, which is just the zeros on the evens, and we have another subsequence, which is just the ones on the odds. Unless they converge to the same thing. So I think what you're saying is, if you have a family of subsequences that converge to L, so that that family covers all integers. Okay, then can you say again?
I'm saying that in the context of a series.
Yeah, let me write down what you're saying.
If you have a subsequence of that series that converges,
If
then the original series must merge.
We'll look at 1 minus 1. You have 2 times, you have 2 subsequent, goes to third time.
Not in the case of a series, because in each sub-term, all the information is of all the previous terms of the underlying sequence are encoded in information. So. Still doesn't work.
No, the series.
you're saying if you have a sequence of partial sums along a subsequence of partial sums converging, is it true that the original series converges?
Yes, I that's.
Well, the negative one.
So now look at the-
doesn't-
Let's look at the -1 to the k. The partial sums, the even partial sums, even is a subsequence.
But that's, you're selecting only specific terms.
Ah, you're saying if for all, okay. You're saying if for all subsequences.
No, that's.
sig- Oh, okay. So then you're saying if there exists a subsequence? Whoops, I didn't mean that. Tell me what to write here.
You're thinking like let's say you have a sequence A of n. Right?
Yes.
That's okay, alternating -1, 1, -1, 1, right? And then we're choosing the subsequence where we only have -1s, but that's not precisely what I mean.
Tell me what you mean.
I mean that any subsequence of the series converges. So the series is like, okay, A of n is -1 plus 1 minus 1 plus 1. Like,
No, he's not taking like just specific terms from the sequence. He's saying sum up until, if you sum up until the evens.
Are you trying to rearrange the order in which you take them? Or are you keeping the order? You're going from 0 up to some value, but you're not going necessarily from 0 to 1 and then 0 to 2 and then 0 to 3 in your sum.
I can talk about this after class. Basically.
Okay. Do you agree that I'm trying to understand what I tried to write down your question, which was if the sequence of partial sums, but not along all ends, just along some subsequence, converges to a limit. I just want to hear.
I can talk.
Okay.
I'd like to talk.
All right, we'll postpone the question. Yeah. So the answer is in general no, at least to this question, and then you'll tell me what your question is after. Great. Let's try to write this up. Okay. Does it make sense? Does it make sense what we're doing and how we're doing it? Let's see. Yeah, I guess I should write it up. I really wanted to prove 2 more things for you today, and I thought it would take too long if I did it purely in lean, so I was just going to do it in natural language. All right, we'll do one more class on this, because this is important stuff. This is important stuff. So addition is not necessarily commutative, but now we're learning all kinds of things. First of all, these are there are 4 main results about theorems, about series, that I have to make sure I cover, or else you haven't taken a real analysis class. One is absolute convergence implies the series converges. 2 is if you're monotonically decreasing to 0, then the alternating sum will converge. There's 3 and 4, and there's no chance we're going to get to 3 and 4 today. Fine, we'll do it next time. Let's scaffold this proof. So here we are, alternating series test. Let's scaffold the proof. So why does the series converge? How are we going to prove that the series converges? Sure, yep. So let's have a little bounded terms bounded below, which is that for all n, an is at least 0. Let's make that a little homework problem. Oh, I already did. I meant to erase this from the skeleton. Okay, So look at this theorem. It's called antitone limit bound. I think there's a monotone limit bound. Either you already had it in your homework or you're about to have it in your homework. You have a sequence that's antitone and you have an L, and that sequence converges to L. If you're decreasing to a limit that's L, every single term has to be at least L. If you're decreasing and you get below L, there's no way to get back. Okay, so that's a simple proof. I'm sure you can do it. So by apply antitone limit bound to what? I need to feed it the fact that it's antitone, that's HA, and the fact that the limit, that's called a lim. Is there any reason why this is called something different? Let's call that HA and let's call this a lim. Okay. So we know the terms are bounded below. Good. What do we want to need? What do we need to know next? So I got this. Let's get that S2N is monotone. Have S2N mono. Monotone, the function that maps N to the partial sums. So this is the sum K in range 2 times N of -1 to the N, -1 to the K, AK. Need a times there. Sorry. All right, I'll make that into, this is going to be a homework. I'll make it a little homework problem. What's the generality in which this holds? Very simply, if you have an antitone, if you have a decreasing sequence where all the terms are non-negative, it doesn't have to be decreasing to 0. Okay, good. What else? I guess we have N2N plus 1, S2N plus 1 is antitone. This is antitone. When I go not to 2N, but 2N plus 1, that'll be by, again, induction, together with the fact that the terms themselves are non-negative. Then what? How about, oops. I see. I just need to slide this over. I don't know a good place to break it. I'm just going to slide it over a little. It's annoying me. Have S2N is bounded. For all N, this thing at N, well, so then I can just drop the function. This thing is bounded by, what did we say it's bounded by? A0. Okay, so that's going to be a little theorem. Have S2N plus 1 is bounded below. For all N, the same thing. Yeah, okay. The same thing, but with 2N plus 1 is bounded below by 0. Okay. So the sequence of partial sums is bounded, on the evens is monotonically decreasing and bounded. Therefore, have S2N is Cauchy. This is Cauchy of this thing. And why is that? That's is Cauchy of monotone bounded, where I need to feed in what? I need to feed in the bound, that it's bounded is S2N bounded, and I need to feed in that it is, what do I need to give this thing? It wants to know that it's monotone and that it's bounded. Okay, so the monotonicity is S2N mono. No? Is it the other way around? It wants the bound and then the monotonicity? Oh, come on. Is Cauchy of monotone. I didn't type it right? I'm going to copy this. Is Cauchy. Oh, the hypotheses. S2N. And which one do I want first? The monotonicity. The monotonicity. And then S2N bounded. Okay. All right. That's the Cauchyness of that. And hence there's a limit. have S2N lim is seek conv. I should give this a name instead of let S2N be the sequence that does this. That'll be much nicer thing to say. So S2N is monotone, S2N S2N at N is bounded, then S2N is Cauchy, and then S2N converges. This is what by apply what? If you know that it's Cauchy, then seek conv of is Cauchy, S2N Cauchy. Okay, so S2N has a limit. Then we do the same thing for S2N plus 1. Let me state the last thing before we move on. And again, I'll add these to the important things I'll add to the homework. So we know that S2N is bounded is monotone and bounded above. We know that S2N goes to L. Let's state this last lemma. The last lemma is well-definedness of the reals, coherence of the reals. I don't know. So theorem, this is add to homework. I'll add have S2N plus 1 lim is seek conv S2N plus 1. By sorry, of course I have to say what S2N plus 1 is. It's the same thing, but going up to one more. And then I can make this look a little nicer. And I can make this look a little nicer. This is evaluated at N. Okay. So S2N plus 1 also converges. And now what's the theorem? Add to homework the theorem. Coherence of R. Well-definedness. Coherence of the reals. So if I have two sequences of real numbers, HA, and I need, I guess, L and M are real numbers, and I guess the sequences I can infer from context, so I shouldn't have to give them explicitly. So seek lim AL, HB is seek lim BM, and then HAB is the fact that seek lim, the function that takes n and sends it to an minus bn, and that goes to 0, then L is equal to M. Okay, so that's coherence of the reals. And if we take coherence of the reals, so what goes to what? I guess I need to obtain L. So choose LHL using S2N lim, and choose MHM using S2N plus 1 lim, and then HL is the one convergence, HM is the other convergence. And why is the difference? Okay, so we have another diff 0, which is seek lim, the function that sends n and maps it to S2N n minus S2N plus 1 at n goes to 0. Again, that'll be a little homework problem. And diff 0. Div 0 says L is equal to M. Okay, so have HLM that L is equal to M. Beautiful. You guys following? Everything makes sense? No one's lost? Okay. And what's the last thing that we need? A little lemma that says, so again, a little homework lemma, theorem, evens, odds, I don't know. Series. What do you want to say? How did we say it here? How did we say it here? It's true for any sequence. It's true for any sequence. That's true. That's true. If you have an even subsequence and an odd subsequence that have the same limit, then, and again, it's true if you have any subsequences, any family of subsequences that eventually cover the naturals, but we don't want to try to figure out how to say those kinds of things. Should we just prove it directly? Maybe we don't need a lemma for it. No, it's good to have a lemma like that. Is it or isn't it? We have a sequence theorem. What? Sequence, seek even odd. That's what we're calling it. So we have a sequence and a real number L, and we have HA2n, which is seek lim, the function that sends n and sends it to A of 2 times n goes to L. And the same thing with 2n plus 1, A2n plus 1 also goes to L. Then seek lim AL. Did I get the parentheses right? Looks like I did. And A is also inferred from these two conditions. Okay, so seek even odd. So now we're going to have seek even odd. It takes 2 inputs. The first input is that the even sequence goes to L. That is HL. It doesn't see that S2n. Ooh, it doesn't see that S2n is the original sequence at 2n. Ugh. Close enough. What do you think? All right, we need another stupid little lemma. Have S2n is for all n S2n, what I called S2n of n is equal to Sn of 2 times n, where Sn is just series A at 2n. So can I rewrite this at, can I rewrite this at, maybe I have to say it as a function. As a function, this function is equal to the function that sends n to that. Okay. Rewrite S2n is at HL. Now it takes HL. Very good. All right. We're going to have to do the same thing. You see what I'm doing? Hopefully you see all the hoops that I'm jumping through. And this is the kind of thing where in game mode, I think it's much harder to do this. Well, especially because I don't want to, if each of these sorries is a homework problem, I don't want to presuppose that you knew the statements or where the statements were going to come from. So I wanted to come up with the statements organically together. Okay, and we're basically done. Maybe I can just apply this. No, apply's not over. We still need the fact that A2n also converges to L, and that gives us that the series converges, but the series converges means that there exists an L. So use L. And now we want to know seek lim, so now apply this. And you still couldn't do it, of course, because I haven't told you what the other thing is. You get the point. I'll finish this off and post it, and in addition, I'll post the homework. See you next time.